The next talk will be on quantum computing, and especially the entanglement issues that are related to cryptography and lots of other interesting future things. And with us today is Stephanie Wehner, a student at the CWI in the Netherlands and working on quantum computing. Welcome, Stephanie.
Well, good morning on this last day of the conference. This is going to be part 2, really, of my talk that I gave at What the Heck. But in case you weren't at What the Heck, this is going to be self-contained, so don't worry. I'm mainly going to talk about games today because, well, it's the last day of the conference. You're all just as tired as I am, and some more entertainment is probably good. Okay. I'm first going to talk about qubits again for the people who weren't there at What the Heck. And then I'm actually going to get to the part that I really want. Namely, I'm going to talk about entanglement, which is a very bizarre phenomenon. And I'm going to talk about something called action at a distance. And okay, better? Okay. And then I'm going to talk about why this is so special, what's the whole big deal with entanglement. And finally, I'm getting to the part that I really want to get to, namely playing games with entanglement. And finally, I'm going to talk about some applications in the area of quantum computing, and mostly in the area of quantum cryptography, referring back to my talk at What the Heck. Okay. Probably many of you have by now seen this a few times before. Classical bits are just 0 and 1. But quantum bits have the funny property that they can actually be 0 or 1 at the same time in what is called a superposition. Only if you measure this state, you will actually collapse it to one of these things. I'm going to talk about more in a second. There's one important property to remember about qubits that makes them different, is that they cannot be copied. And in this talk, I'm not going to write 0 or 1, but I'm just going to use 2 directions, or 2 colors, you can even think of them, like red and blue. Okay. I said that qubits can be in a superposition of, say, 0 and 1. And only if you measure the state, you will actually view a 0 and view a 1 with a certain probability. The state we set up here has the property that if we measure it, we will see a 0 with probability half and a 1 with probability half. That's all you really need to remember about qubits for this talk. And an important point to remember is that after we performed this measurement, the qubit is actually not longer in this state. It has actually collapsed to what we observed. So if we saw a 0, then this will be the state after the measurement. And if we observe the 1, then we'll be over here. Okay. People at What the Heck have seen this slide before. I will not really need this much in this talk, but I will refer to it briefly later. So this seems pretty arbitrary. You can think of this as polarization directions of a photon, and it seems pretty arbitrary that we just choose, say, up and horizontal and vertical. We might, for example, also choose these 2 directions. That really doesn't matter. I will use this symbol to say that we measure in this basis. And what does that mean? You can think of it, maybe a lot of you have been doing some computer graphics, is for the purpose of this talk, you can think about if I measure in this basis, that means that I really project on these 2 directions. And for a different basis, I just have 2 different directions. This is pretty much arbitrary. I could have rotated this by 60 degrees, and we could still do exactly the same things. Because suppose now I have a qubit in this basis, say the diagonal basis, the red here, then I can, of course, re-express it in a different basis very easily. Because I can see, okay, it's like here, so I have a component of this part, and I also have a component of the lower part. Now, there's really only one important thing to remember for now, is that if I measure in the same basis, say if I have a qubit which is in a certain state, in a specific state, namely prepared in a 0 state, and I measure it in the same basis that I prepared it in, then nothing happens. It'll just remain unchanged. And likewise for any other different basis that I might choose. So if I measure in a different basis, suppose I now pick the diagonal basis, and remember that we could, of course, express it in terms of the other two directions. In that case, you can see, okay, I have what this means here is that I will observe this part with probability half, just what I have here squared. So in this case, if I measure it in the wrong basis, I will see a 0 with probability half and a 1 with probability half. And likewise for, say, the 1. And I can play this game with all the other states as well, of course. So for this one, of course, this is now a state in the horizontal vertical basis, but of course you can also see that you can express it in terms of the other basis. Okay. Now, at what the heck I was talking about in the beginning of my talk about an effect called interference, which I'm not going to talk about now at all. Instead, I'm going to talk about something very bizarre, namely entanglement, which I hardly told you anything about at what the heck. So at what the heck, I only briefly mentioned that there is something called entanglement. So I'm going to use two players now, Alice and Bob, and they share a state, which means that they both have a qubit. You can think of this as some photon that they hold in their hand. And these two photons are in a certain state called an entangled state, which means that they're correlated in this way. Now, what does this mean? Now, at what the heck, I was saying that if Alice measures this state, she will observe red with probability half and blue with probability half. So this is, you can just look at this, it's just the same as before. So we have square root 1 over square root 2 here, so it's probability half. And just as before, measurement changes the state. So if Alice, for example, now, just suppose she saw a red when she did the measurement, then the state after the measurement will actually be just red, red. So in fact, if Alice sees a red, then she knows that Bob, whenever or how far away he might be, also measures this state, will exactly also see a red. She just knows this. And of course, you can play the same game with the other outcome. And Bob will, again, if Alice saw this blue, then Bob will always see blue as well. Now note, though, that actually we haven't transferred any information. Only Alice knows what Bob's outcome will be. Okay, so this is all I had said at what the heck. But you might argue, okay, maybe let's be a little bit more skeptical about what's going on here. I mean, it seems almost like, okay, we can just accept that this is the way it works and then all will be fine. But maybe let's think about this a little bit more. What's actually going on here? So we have these two particles, say Alice has a photon and Bob has a photon. But how does this actually happen? Why does this happen that if Alice measures her photon, then suddenly, even if Bob is, say, far, far away, actually Alice's measurement has an influence on his photon far, far away? So you could argue, so maybe actually there's really some communication going on. So you can test this. Let's just say we put Alice on Earth and we put Bob on Mars. And somewhere in the middle here, we put some spaceship which emits two photons. And we require that immediately upon reception, Alice measures it, and Bob does the same immediately upon reception. And then we ask him, okay, what were your outcomes? And we do that many times, and we'll in fact see that it's really true. If Alice sees red, then Bob will see red, and if Alice sees blue, then Bob will see blue. So if we accept the fact that there's no faster than light travel, or also no faster than light communication, then clearly there must be something else going on here than just this particle somehow sending some information secretly outside of our view. Okay, so let's try something else. Now I've said that Alice has some chance of obtaining a certain outcome. It's not exactly clear what this means, right? I mean, in fact, it does not mean that has this already been determined? Because maybe far away in the past, say this is nature, Nature has in fact already decided whether we're in the blue or in the red case. We just don't know it yet because we haven't measured yet. But really, it's there all along. Okay, let's presume that this is correct. It's really nice because, of course, if we assume that this must happen, of course, because it's been, say, blue all along, and once Alice measures, she just discovers it's blue, and of course, Bob once has to be blue as well. And exactly, if we do this many times, we will even observe the same statistics, because we say that, suppose for every such pair, nature flipped the coin, and with probability 50%, she says, okay, that was going to be blue, and with probability also 50%, she said it's going to be both red. So this fits what we see here perfectly. But let's examine this a little bit closer. So basically what would happen in this case is that nature beforehand already, with this particle, associates some kind of, I don't know, instruction sheet or cheat sheet where it says, okay, if Alice measures in this basis, then output this. And if she measures in this basis, then the output is going to be that. And likewise for Bob's particle. So you can think of this as, this photon is just going to be enclosed in some box, which comes with some kind of instruction sheet, and that's all there is to it. Okay, so this is really no big deal then. I mean, there's nothing really mysterious about this. And so how do we know that this is the case, or maybe it's not the case? And like I said, I want to talk about games. So in fact, I want to look at this whole procedure now as a game. And of questions and answers. So we are now going to play against Alice and Bob. These measurement settings are going to be the questions. So we're going to play a really simple game where we just ask Alice and Bob 2 possible questions, 0 or 1. And likewise, there's only 2 outcomes for now, namely also 0 and 1. And the instructions that were given, say, beforehand by nature, you can see these as the strategies of the players. So they're going to say, okay, before the game starts in, they're going to talk to each other, and Alice says, okay, Bob, if I receive this question, then I'm going to say this, give this answer. And likewise, Bob, okay, if I get this question, then I'm going to give this answer. And they just agree on that. Okay, so we're going to impose some rules on this game. First of all, of course, we're going to tell the players what game we're playing in advance. It's maybe clear, but then before the players start, we allow them to go into a secret room and communicate all they want, so they can, in particular, generate these cheat sheets. And once the game starts, we don't allow them to communicate anymore. We can enforce this by, say, flying Bob to Mars and leaving Alice here on Earth. Okay, so in fact, here I want to play a 3-person game because it's easier to think about, but it's actually just the same thing. Only we have 3 parties now. And say we're going to put Alice on Earth, Bob on Mars, and I don't know, we put the cat in some spaceship in the orbit around Jupiter. And we're going to ask them questions. And they're really just going to be 0 or 1 questions. So we're going to ask Alice question X, the cat question Y, and Bob question Z. And we give them a promise, namely we're going to only choose questions thus that the sum of the questions mod 2 is just 0. May seem a bit obscure, but let's just assume we've played a simple game. You can play other games too. Okay, and we're going to say that Alice, Bob, and the cat win if they can give us answers A, B, and C, such that the OR of these questions is going to equal the sum of their answers. Just set it up this way. And otherwise they lose and we win. Okay, clearly if we would have communication, then it's clear that they can win the game. They can tell each other which questions we ask, and then they can pick A and B and C in accordance with our requirements and win the game always. So let's make sure they can't communicate, but putting them far apart. Okay. Oops. So this is a table of the possible questions which fit which we can ask. So we pick just one of these at random, and we're going to ask, say, Alice 0, the cat 0, and Bob 0 in this case. In this case, we'll ask Alice 1, and the cat 1, and Bob 0. And these are the possible answers that they could give. So this is like the first one corresponds to Alice's answers, then Bob's answer, and then, the cat answers, and then Bob's answers. And so for this question, only these are winning answers that they could give us. And for this one, so here the OR is obviously 1 in all these cases, so then we always have these answers as possible winning answers. Okay, so let's just forget about entanglement for a second and think about some strategy that they might want to play. For example, they might agree that, okay, Alice is just gonna give exactly the same, take the question and make the answer the same as the question. The cat is going to take the not of the question. So if she receives a 0, then she's gonna answer a 1. And Bob always says 1. Whatever we ask doesn't matter. Okay, so let's just see how this naive strategy performs. Suppose we gave them the 0, 0, 0 question, then they actually win the game here. And likewise here, they also have a winning strategy. So what happened here is just, suppose this was the question, then of course Alice is just going to return the question, the cat gave the not of the question, and Bob's always going to say 1. So this always works great, except for this case. So in that case, they will lose. Okay. So note that if we pick just one of these at random, then they're going to win 3/4 of the time. Okay. Now, let's think about what they could play. Let's assume that the world really works like that we have cheat sheets. Really, everything is already determined, we don't know it yet. The cat has some kind of sheet where it says, if I receive a 0, then I'm going to answer 1, for example. If I receive a 1, then I'm going to say this. Suppose that this is really how it works. In that case, we can actually determine that they cannot win all the time. Now, why is this true? Now, this here means, I'm using notation here a little bit. So this actually means that A of 0 is the answer that Alice will give upon the reception of question 0. And likewise, this is the answer that cat is going to give upon the reception of question 0. And in this case, remember that we had this requirement. We can actually reason by just summing up all these things on this side and on this side. This would actually require that 0 equals 1. So clearly, there is no assignment that we can make here, which would always allow us to win. Excuse me? I can't hear what you're saying.
The laser pointer isn't visible. Can you please use the mouse cursor? I assume it will not be visible on the video after the Congress.
Okay.
Thank you.
Okay. Okay. All right. Okay. So in a world which consists of these cheat sheets, they cannot win all the time. Okay. I'm not going to through how this works exactly because it's easy to look it up because it's a very well-known game, namely the GHZ game. If there exists a certain entangled state that they can share beforehand, remember we allowed them to talk together beforehand, so they might also go and share whatever state they want, then there exists a strategy, namely all they do is if they measure a 0, then they're going to measure in one basis, and if they receive a 1 question, then they're going to measure in the other basis, and they just take their measurement outcomes as the answer. And in fact, it turns out that in this case, they win all the time. 100% of the time. We can run this 1,000,000 times, and they will always convince us. So clearly, from this, we must conclude that maybe something else is going on. Remember that communication was not possible. We put them so far apart to make sure this can't happen. Likewise, entanglement itself can't allow you to transfer any information faster than light. And yet they can always win. So from this we can conclude that really qubits are different than these boxes with predetermined instructions. And these predetermined instructions are sometimes also called hidden variables, in fact. And this might seem a little bit obscure, but it's actually, if you think about it for some time, it's actually quite weird. And so there are many such games. The first one really was by Bell, and there's many games like this afterwards, which really show that there is something different going on in quantum mechanics than these classical predetermined instruction sheets. Okay, this is great. I probably find this entertaining enough, but probably I should fabricate some excuse why this is also interesting. So basically we saw that quantum entanglement allows you to do things which would otherwise need classical communication. In this game, they were only really allowed to, could only win all the time if they were able to communicate. But we've taken the communication away. So in fact, entanglement really allows you to solve a problem instead of using classical communication, sometimes. Namely in this kind of coordination type of games that I was just talking about. And in fact, it plays a very important part in quantum algorithms. And in fact, it's been shown by Noah Linden and Richard Josa that quantum speedup is really only possible due to entanglement. And you can play some other cool things with it. Probably you heard about quantum teleportation. And in fact, what I said in my last talk at What the Heck can also be viewed from the perspective of quantum entanglement, which is what I'm going to talk about in a second. Okay, quantum teleportation is a pretty cool thing. Suppose that Alice and Bob really share such a say EPR pair, such an entangled state. They've maybe distributed that beforehand, or we give it to them. Anyway, it's there. So using this, they can now actually send an arbitrary qubit. In fact, they don't even need to know anything about this qubit, from Alice to Bob, using just one EPR pair and 2 classical bits of communication. Now, I said that information cannot be transferred faster than light, which is actually why these two classical bits come in. So Alice has some kind of qubit. And she performs a measurement on this, a joint measurement on this qubit and her part of the entangled state, from which she gets 2 measurement outcomes, which she transfers to Bob. And after that, so they've used up this entanglement, the qubit is actually over here to Bob. And you can play this over arbitrary distances in theory. So this is really quite a cool thing. Now, I also said that it has some applications to cryptography. Now, first of all, I want to say that it also has a negative application to cryptography, namely that in classical cryptography, there's often protocols whose security depends on the fact that certain parties cannot communicate during the course of the protocol. But of course, with entanglement, maybe they can still achieve some coordination, which would otherwise not be possible. For example, there's a notion called interactive proof systems, where you have a certain a few provers, and they're trying to prove something to you, which you cannot decide yourself. For example, maybe they want to prove to you that you can color a certain graph for 3 different colors. That means that you can assign a color to each node in the graph such that no 2 adjacent nodes have the same color. Maybe they want to prove that to you. Now, classically, if they cannot communicate, that you can ask them questions and you can say cross-check between them. But really, they really want to cheat on you, and you can phrase this as some kind of game. And there, in fact, it turns out that entanglement makes a very important difference. So you really have to think about what does it mean for classical protocols if suddenly you allow quantum adversaries. And of course, there's some positive things about quantum cryptography, namely what I was talking about last time, namely quantum key exchange. And here I want to talk about an entanglement view on quantum key exchange. So, for the people who weren't there at What the Heck, the problem we are really trying to solve here is actually very clear. Probably most of you know it already. Alice has some message, and she wants to send it to Bob, but somewhere in between is an eavesdropper who tries to learn the contents of this message. Now, the goal of secure communication is to allow Alice to have some kind of safe, some kind of encryption mechanism which will hide the message contents from any eavesdropper on the way, and then later Bob can open it and get the message. So this safe is great, but probably it requires some kind of key. In fact, it does require some kind of key. So Alice has a key, and let's just assume that Bob has the same key, then they can use this to lock the safe. Now, as long as Eve is ignorant about this key, if she doesn't know what it looks like, she cannot open the safe. But there's a little bit of a problem, because say Alice and Bob are still on Earth and on Mars, where we put them, and but now they want to communicate securely. So how do they get the key across? In fact, if you just send some messages, maybe Eve is going to intercept the messenger, learn the key, and just open the safe herself. So the problem we are trying to solve here really is how to get the key from Alice to Bob. So secret key cryptography has many classical examples. I mean, you're familiar with them: DES, IDEA, AES, whatever. They have an advantage. They're short keys, but really they're only computationally secure. And I mean, they're not really proven to be secure. So the only really absolute secure system is a one-time pad where the key is equally long as the message. Now this seems hugely impractical, of course, because we need to transfer huge amounts of key. But this is really the only system which is later secure. So how does a one-time pad work? It's really very simple. Suppose this is one bit of the message that Alice wants to transmit, and this is one bit of the key. She just takes the XOR of these two things, and sends it over to Bob. Bob, who has exactly the same key as Alice, again takes the XOR and outfalls the message bit. So there's a very simple example where we have the message and we XOR it with a key, so we get the encryption, and then Bob just goes the other way around to get back the message. Okay. Like I said, the problem here is how to get the key across. And you might say, why not use some kind of public key cryptography? I mean, public key cryptography is also based on non-proven assumption, for example, that factoring is a hard problem. And it can in fact be broken if one would build a quantum computer also retroactively. So what we really want is the perfect security from a one-time pad without the need for a secure channel. And this is what quantum cryptography addresses. And last time at What the Heck, I was telling you a protocol how this works, but here I want to view it purely from the perspective of entanglement, which was first done by Arthur Erkert in '91. So let's just make an assumption, okay? We have Alice and Bob and some malicious eavesdropper. And let's just suppose that out of the sky, Alice and Bob would already have 2 qubits which are entangled in this way. Suppose we had that. Then clearly Alice can just measure it, and she obtains a random bit, red or blue, and they'll use this as a key. But we just shifted the problem somewhere else, which is that how are we going to distribute this EPR pair? Let's just try some really naive way. Alice is going to just create 2 photons, which are in fact entangled, and she'll send one of them over to Bob. So great. But remember that there was Eve, so maybe Eve captured Alice's transmission. Or in this simple protocol I was just describing, there's even a worse scenario. Maybe Eve is now entangled, in fact, with Alice and Bob, which means that Eve also holds a qubit, and the total state of the system is going to be described this way. What does that mean? That means that if Alice would now measure, as we did before, then the state would collapse. And if they had agreed that they both would take their measurement outcome as the key, in this case, this means that in fact Eve also only has to measure, and her qubit will end up being exactly in the same state, which means that Eve knows the key, so that's really not what we want. So I'm going to go back to the games now. I'm only going to give you some intuition how this works, because this is really the most important thing, is that Alice and Bob are now going to play a 2-person game, similar to the one we described before. Of course, we're not going to ask many questions now, but so that at every int they pick, do that many, many times, And then they will pick a random subset of these qubits that they've transmitted, and they will test to see whether maybe Eve was present. So the way they do this is they play some kind of game, just the way that I described it before. Now, this time, they're going to ask themselves questions, so they're just going to flip a coin and determine on the outcome of this coin flip, they're going to, say, perform a certain measurement, which we can just label by 0 and 1. It's not very important what these are. And at the end, they can compare. And they can see how often they together were able to win the game. And there's a very peculiar property about entanglement, which is called monogamy of entanglement, which means that one person can never be maximally entangled the same way with two people. So in this case, suppose if we have Eve here, and the state would really be described this way, instead of what we really wanted, namely being in an EPR pair, this means that Alice and Bob will win the game less often, because their correlation, say their entanglement, is not as strong as if they would just have entanglement between the two of them, without Eve. Now, I'm not going to describe the details about this because I haven't introduced anything like operations on qubits or anything like this. But this is the basic idea about this. So if they detect later that maybe they expect to win this game in, say, 85% of the time. Now, if they see that over all these runs, we only achieved like about maybe, 76%. Maybe this is, then they conclude that Eve is present and they abort. This is very similar to what I said at What the Heck, where they also detect that Eve's present in a completely different way. And then they also decided to abort if they detected an eavesdropper. So now if they don't detect an eavesdropper, if they really win 85% of the time, then they conclude that with high probability, they really share the remaining pairs will always also be entangled pairs of this form. And then they just measure and use that as a key. Okay. So, in fact, only what I want to say is that the protocol that I described at What the Heck can actually also be phrased in the scenario. Okay. To summarize, as I already said last time, really, quantum computing really differs dramatically from classical computing, and one of the fundamental reasons for this is that entanglement really is different than classical correlations. By classical correlations, I now mean these cheat sheets that were there beforehand. And entanglement is really the most important, probably the most important thing in quantum computing, which really makes it happen, which makes it so much different from classical computing, and which really is responsible for the great speed up. And there's a lot of interesting questions. I mean, actually not so much is known, especially about if we have 3 players or more players, what's going on in these settings. Okay, this concludes my talk. Are there any questions?
In the GAH game, you said that the 3 players win all the time, but later on you said that if there are 3 players, that it lessens the entanglement between 2 of them.
Ah, right.
I didn't get why.
Okay. Yeah, that's not entirely clear. I didn't say that. That's correct. That's a very good question. But they will play a different game in this case. So they don't play the same game. They will play a slightly different game. In this case, for example, they could play a game where they require that the product of their questions answers the sum of their outcomes. And in fact, they can play this particular game less well if there's going to be 3 of them and just 2 of them going to play this game.
Is there anything to stop Eve pretending to be Bob to Alice and pretending to be Alice to Bob? They might end up with different keys, but they could use that for the rest of the communication.
No. So what I have not actually said here, which I said in my talk at What the Heck, which is quite important, that even in quantum cryptography, actually Eve and Bob are assumed to start out with a very small amount of key. So you can really think of quantum cryptography as key expansion rather than key generation from scratch. And they will use this very small amount of key to authenticate their messages to each other. But the important part is that even if they start out with a very, very tiny amount, from this amount they can generate key till the end of time. Because they can use, so it has been shown that quantum cryptography can be what's called composed, which has the effect in this case that we can take some of the key which falls out of our key generation process and we'll use that as authentication keys for future rounds. Yeah, that's a very good question.
Yeah. Some companies today claim to be selling quantum cryptography products. Yeah, I'm here. So some companies claim that they are selling quantum cryptography products today. So do you know if they're applying the principles that you've just described, or is it just marketing bullshit?
It's not marketing bullshit. They are actually doing what I told you in my talk at What the Heck. This is a view on quantum key distribution, which is mostly, say, if you phrase it in the entanglement picture, which is mostly useful to prove security of protocols. But no, I mean, it's not just bullshit. I mean, of course, in practical implementations, so this quantum key distribution has been proven secure in these beautiful pictures where we have these tamper-proof boxes basically at each end. But there have been some completely practical attacks where, for example, a device was not properly shielded and someone was able to shine a laser back into the quantum crypto device and just by the reflections figure out, for example, the alignment of the polarization filter inside this box. Of course, this is assumed to never happen in these ideal models, which are proven secure. So, but I mean, these boxes really do quantum cryptography. I mean, there might be some, say, practical problems, but I think they can be addressed. I think the most important practical problem really right now is that they cannot generate key fast enough. So what actually these boxes do is they don't do what I just said and generate a one-time pad. They will generate keys successively, smaller keys, and then use AES, for example, to encrypt the traffic using these keys. So it's far from ideal, that's true. Yeah. But yeah, I guess they're still working on it as well.